Hey guys, welcome back. In this video, we're going to do buffers. We're going to talk about buffers, and we're going to start with an example to explain buffers. And the example is, what is the pH? There's the question of a solution containing 0.1 molar acetic acid and 0.1 molar sodium acetate. And gives you Ka for acetic acid. All right. And so if you notice, I already have the equation written out, and you write the equilibrium for the weak electrolyte. Well, okay, so acetic acid, you know this is a weak acid. And sodium acetate, that's a strong electrolyte because it's ionic and aqueous. And so we don't need to worry about that one. All right, reforming. And so what we're going to do is, in this, we're going to point out this arrow here, and we're going to say that the equilibrium lies on the left. Right? Because we have a weak acid. We've got a weak acid. Acetic acid is a weak acid. So this Ka expression, right, means that we're going to have more acetic acid in solution than we will adronium and acetate. That's what that means. All right? And so for our weak acid, we got 0.1 molar. All right? And so we're going to say that our 0.1 molar, whatever it is going to be here, right? We're going to have 0.1 molar. That's our concentration of acetic acid. But we also have 0.10 molar sodium acetate. Try to make those about the same size for us. And there we go. Close enough. Maybe a little. There we go. All right. And so now what we're going to do is we're going to make two assumptions. We're going to assume all of the acetic acid, right, all this, right, is due to the acetic acid originally present and not due to the hydrolysis of the acetate from sodium acetate. All right. So what we're saying is that most of the acid stays as acetic acid. Yes, some goes, but most of it is going to stay as acetic acid, and we're going to ignore any hydrolysis, any of this reaction happening, right, from the sodium acetate. We're just going to ignore it. We're saying don't worry about it, because the little of this that comes over is equal to about the amount of this that goes forward, because K is small. But on the sodium acetate side, we're going to assume all of the acetate is due to the sodium acetate in the solution, comma, and the amount of acetate from the ionization of acetic acid can be ignored. All right. So that's what we're going to assume. All right. So those are assumptions. Now, our weak electrolyte Ka will be equal to hydronium acetate, acetic acid. And so that gives us 1.8 times 10 to the negative 5. We don't know the hydronium concentration. We know acetate's 0.10 molar. And we know acetic acid's 0.10 molar. All right? And so what that means is that the concentration of H3O plus is equal to Ka, which is 1.8 times 10 negative 5 molar, because those cancel. All right? So that means the pH is negative log of H3O plus, which is the same thing, in this case, the negative log of Ka. Right? And so if you do that, the pH is 4.74 if we do the math, or what we call the pKa, right? The pH equals the pKa at this point. All right? This is an ideal buffer. It's an ideal buffer. All right. And a buffer resists pH change by neutralizing added acid or base. Either one. It does either one. All right. And so if you notice, we have equal amounts, all right, equal amounts of acid and conjugate base. And so that's what we have here, and that's kind of important for our buffer system. All right. So now let's look at some examples, and we're going to look at the buffer in its two parts and then what happens overall. All right. So for buffers, let's just consider 0.1 molar acetic acid. So we're going to just have the weak acid. All right. So if we have 0.1 molar acetic acid, I'm going to have lots of this, right? 0.10 molar, which means we have quite a bit. Lots. All right? And that means over here, we have a little bit of that and a little bit of that. All right? So over here, we're going to have very little. And that's because Ka is small, right? Remember, Ka, 1.8 times 10 negative 5. That's small. So there's two things that can happen here, all right? Just two. We're going to add acid, or we can add base. So let's take the base example first. What happens when base is added? So if we add the base, what happens? Well, OH minus will combine with what? Well, what's OH minus going to combine with? Well, it's going to combine with hydronium, right? And how do we know that? That's 1 over Kw. That's the constant, all right? Hydronium and hydroxide meeting up to give you 2 waters is the opposite of Kw. And so 1 over Kw, right, that's 10 to the positive 14th. That's a huge number. So OH will combine with hydronium, all right? That means what we do here, it removes hydronium from the system. Well, that means the reaction shifts to the right to products. All right? Not right. Right to products. It does, right? To restore equilibrium. Well, there's plenty of weak acid to go to do this, right? There's plenty of reactants. Since we have lots of reactants, the pH does not change much. All right, because we got lots of this acetate or acetic acid in solution. Okay. So we can, if we remove this guy, it's gone. There's plenty of this to shift over. And so as this removes, there's plenty to come over. More removes, plenty to come over. More removed, plenty to come over. And it doesn't change the pH much because the ratios aren't changing. Just a little bit, not much. But then the question is, what happens? We'll just do this 1 and 2. When acid, or H3O plus, is added to our system. Well, if we add acid, we're actually adding here, right? We're making this bigger. Well, that's a problem. So as this goes from small to bigger to bigger to bigger, right? Now we have lots of this. Well, the reaction is going to shift left. Problem is we don't have much acetate, all right? So our acid, H3O plus, combines with acetate, and reaction shifts left to reactants. All right, problem, acetate, that's horrible. Let's write a little neater for you guys. Acetate is quickly used up, or quickly consumed, and that means the pH rapidly decreases, right? It's more acidic, right? More acidic, more hydronium in there, all right? So what does this mean? That means the weak acid resists the change of base, all right? Weak acids offset the base. Now, the next option is sodium acetate. So now we have lots of acetate in solution, and we have a little tiny bit of acetic acid. All right, we got 0.10 molar, so we got lots, and we have very little. All right, and then why we have that, Kb is small, which is 5.6 times 10 to the negative 10th. So not a lot coming over, right? So back to number 1. What happens this time when base, our hydroxide, is added? Oh. So what happens? All right. Well, there's very little acetic acid to react. Right? There's really little acid to react, which means the pH will rise quickly. Right? There's not much of this. So when we add hydroxide, even if it takes away the hydronium, right? Let's say it's going to take away hydronium, right? There still has to be some here. So if it takes that away, we got to come back over. And then base takes it away, and we come back over, and the base takes it away. Well, the problem is there's not very much of this to take of this acetic acid to come over. So it can only do it a little bit, and then boom, it's gone, and you no longer have the equilibrium. You destroy your system, and it's just you're adding base to the solution. So that's what happens when you add base to the conjugate base. 2, what happens when acid, hydronium, is added to our system here? Well, there's plenty of acetate. All right, plenty of acetate to react. The reaction shifts left to reactants, and the pH does not change much. All right. Okay, and so let's recap this real quick. So we have the acid. If we add base, right, and remove hydronium, right, so that little hydronium, we remove it, we can refill it. Remove it, I can refill it. Remove it, we can refill it. So the pH doesn't change much until this 0.1 molar gets whittled down to less, right? pH doesn't change much. However, the acid adding here, make this bigger, it's a problem because there's not much of this to react. For the conjugate base, let me write that down. This is the conjugate base, right? Acetate. We don't care about the sodium because there's no hydrolysis there. Right? And so you have a base here. When we add the base, right, it's going to remove this, what's little there, and there's not much to replenish, right? It's, right, again, going to remove that, not much to replenish. So the pH just goes up because there's a lot more hydroxide now. However, when you add this guy, there's plenty of this to react, come over, restores. Add some more of this, plenty to come over and restore. So the conjugate base does not get overwhelmed with added acid. So in summary, so we're going to summarize this. The weak acid resists a change in pH. Right, upon the addition of base. We add base. So if you add base, the weak acid can handle that. The conjugate base resists a change in pH upon the addition of acid. All right. So that means, so for complete buffer action, right, we want equal amounts of acid and conjugate base. All right. So you want equal amounts of both. All right. That's what we want. So if we look at this ideal, so we have acid and we have conjugate base. And we have equal amounts. All right. It's a 1 to 1. All right. And that's where the pH equals the pKa. Now, just a side note here, this is always going to be acid conjugate base. It doesn't matter if you have a weak base and it's conjugate acid. We always look at it from the hydronium and the acid point of view. So if you had ammonia and ammonium chloride, let's say, or ammonium nitrate or whatever you had as the salt, so you had ammonia and ammonium, you would still write it as ammonium and ammonia would be the conjugate base, and ammonium would be the acid. That's how we just do it, okay? All right? We have ideal, we have good, and we can work. So when we talk about the amounts of acid and the conjugate base, so it's 1 to 10 or 10 to 1, right? That means the pH equals the pKa plus or minus 1, right? So if your pKa is 4.74, this means it'd be 5.74 or 3.74. And can work would be 1 to 100 or 100 to 1. And this is where your pH is plus or minus 2 pH units from the pKa. All right? And so you have to look at the pKa of your buffers to decide which one you need, if that makes sense. All right? And so we want, if I want a pH of 10, I would not use acetic acid because that's a pH of 4.74. It can't be a buffer in that region, all right? The buffer region all right, is 2 pH units from the pKa. All right, so you might want to think about this as, right, yeah, this is right wherever the pKa is. So if your pKa was 5, you could be 6 to 7 here. You could even work if the pKa was 5. It could be between 7 and 3. Between 7 and 3, right? But ideally, this is better. Obviously, that's the best. Okay, so that's what a buffer is. It resists the change of pH. All right, if you add acid or base. All right, because when we talk about chemistry, sometimes the pH is a very important condition for things, and we want to design a system that can resist the change of a pH if needed. If we add acid or base, because a lot of things now, as you learned, are acids or bases, at least weak ones. They're either proton donors or acceptors, and if I'm a proton donor, I'm a proton acceptor, I'm going to affect the pH. And so sometimes our systems need to maintain a constant pH or a very, very constant pH, and so you got to be careful of that. All right, so that is what buffers are. If you have any questions, let me know. Otherwise, we'll see you the next time, guys. Take care.